So, good evening, students. Uh, in this session, we are going to discuss some concepts in calculus, which it includes Jacobians and extreme values of functions of several variables when we are dealing with. So, that we try to discuss about. So, see here all these things we have discussed. Yeah, we'll go to the idea of Jacobian in dealing with transformations. So, what is a Jacobian? So, if you have see, for example, there are transformations. Say like yeah, say you have a function of say x comma y, and v is a function of x comma y. Then the question is that how we are defining some, first of all, a matrix called Jacobian matrix that is defined as dou u dou x, that is we write as u subscript x, dou u dou y, and we have dou v dou x in the second row, dou v dou y. So here we have two functions involving two variables. So there are two variables. They are x and y. So this is called Jacobian matrix ux, uy, vx, vy. This is called Jacobian matrix. Jacobian matrix. And the determinant of this Jacobian matrix is known as Jacobian. So, and the determinant of this Jacobian matrix, that is how we write the determinant of the Jacobian matrix is in fact this ux, uy, vx, vy. So we may represent this as a determinant, represent like can be written like this, and sometimes we write this in this is a function of two variables, real valued function of two variables, and so sometimes we represent this in like this. So this is, and some people say write this as j. So this idea, see whatever we have written here, this idea is known as sometimes we will call it transformation. So this is the Jacobian matrix of the transformation, and the Jacobian is the determinant of that matrix. In a similar way, if we are dealing with the three functions of three variables, if we are dealing with the three functions of three variables, like you have a function u, which is a function of x, y, z, and we have a function v. It is again a function of x, y, z, and we have w. It's a function of x, y, z. Then we can think about, so this is also a transformation. We can think about its Jacobian. So how can we represent that Jacobian here? We represent that Jacobian as j is equal to dou u v w by dou x y z. This is how we represent the Jacobian. So this is nothing but you can write like ux uy, I mean subscript y means do you do y, do you do z, similarly do we do x, do we do y, do we do z, do w do x, do w do y, do w do z. So now see, yeah. So what is the use of this Jacobian? See, it determines when you have, suppose you are dealing with two functions involving two variables. What some of the uses I would call applications, how we say. So if we have this transformation, look at its j, that is do u v by do xy. It is expressed in terms of x and y. So there are two possibilities now. What are those possibilities? J, this j can be equal to 0 and the other one is not equal to 0. If j is equal to 0, that a determinant is 0, then we say u comma v are functionally dependent. Functionally dependent. That is, there exists a relationship between u and v. That is the meaning. If the determinant is not equal to 0, then we say u comma v are functionally independent. That is, there is no relationship between A and B. There is no relationship between A and B. So, one case is functional dependency. This is with regard to this one. And the other one is functional independency. That is when you have like this, it is this. So functional dependency and independency. Suppose now see, I say, uh, good, right? I say, see here, U is, sorry, I say, okay, U is, U is equal to, say, right, say, for example, uh, good. So cos x, okay, right, cos x, U is say cos x, okay, okay, just a minute. We say sin x. So now see, you look at this transformation. There are two variables. The and each is a function of say two variables x and y. U of xy is cos x. V of xy is sin x. Then see, look at the Jacobian of this. That is, if you write like this, dou uv, dou xy, then what we are getting, see, the formula says ux, uy, vx, vy. If this is our formula, then this is equal to what is ux here? Because u is cos x, so dou u dou x is minus sin x. And what is uy? uy is dou u dou y is 0. Similarly, what is Vx? Vx is cos x. And what is Vy? Vy is 0. So the determinant is 0. So now see, in fact, this is true for any value of x and y. So what we got here in this circumstances, dou uv by dou xy in this scenario is we got as 0. Right? So what did we say here in this chart? Then they are functionally dependent. I will show how they are functionally dependent. What we mean by that functional dependency. So if you see from here, if you see this idea, okay, one thing please see here. What is u square plus v square? U square plus v square is cos square x plus sin square x. See what is our ux? U cos x, v is sin x. So this we know from trigonometric identity, it is 1. So we are able to see a clear relationship involving u and v. This is what we mean by functional dependency. Functional dependency between functional dependency between u comma y. On the other hand, we'll take another example. See here, we take, say for example, u is say x cos y, v is x sin y. So in such a case, the Jacobian we would like to calculate. The Jacobian we would like to calculate. What is the Jacobian here? J is equal to uv by xy. That is equal to, again if you apply the formula ux, uy, vx, vy. So this is equal to, in our case what is ux? In our case ux is cos y. Ux is cos y. What is uy? Uy is minus x sin y. That is dou u dou y I am talking. What is Vx? Vx is sin y. Vx is sin y. What is Vy? Vy is x cos y. X cos y. So if we take the determinant here, is equal to x cos square y, that is x cos square y minus into minus plus x sin square y. X sin square y. So it is coming as x into cos square y plus sin square y. And we knew that it is x. So what did we find here? We found that dou uv by dou xy is x. That is what. So It is not identically equal to 0. It is not for identically equal to 0. So see here, for example, if I ask you what is dou uv by dou xy, this scenario when xy is equal to say 1 0, the response is 1. If we ask what is dou uv by dou xy at xy is equal to say 2 1, then it is 2 because x value only it will come. So it won't be identically equal to 0. So what can we say? Therefore, u comma v are, there is no relationship here, functionally independent. They are functionally independent. So here I can clearly say that, this is not equal to 0. This is not equal to 0. So for some values of x, it is not equal to 0. Therefore, they are functionally independent. So we have seen an example of two functions which are functionally independent, and we have seen examples of two functions which are functionally dependent. If they are dependent, we see that there is a explicit relationship between u and v. That is, they involve only u and v. They don't involve x and y. Here, explicit relation means u square plus v square is equal to 1 means that relationship does not involve x and y. On the other hand, if you see, here also we got some kind of, okay, here you have x. Because this is not equal to 0, what we can assure is that we cannot expect a an explicit relationship involving u and v only. That is what we can say. So that is one of the most useful properties of, most important properties of Jacobian. See here, what it says is that one more thing. If you look here, you can say that, for example, see here, uh, right. If you take this, that is, I would like to say one more thing here. So what is here? It is u is equal to x cos y and v is equal to x sin y. This is what it is there. So from these two things, we can get, okay, uh, we can get, right, what we can get is that tan y is equal to, okay, tan y is equal to v by u. Tan y is equal to v by u. That is one thing we can get. Further, you also see that u square plus v square is equal to x square. So you can say that x square is equal to u square plus v square. So somehow we are able to write y explicitly in terms of u and v, and x also in terms of u and v. How can that be done? So if you take this, see here. So what can we see is that y is equal to y is equal to y is equal to tan inverse v by u, tan inverse v by u. And x is equal to, you can choose one thing, either plus u square plus v square square root or minus. So we have taken x as plus. In such a situation, what is happening here is that we are able to express x and y explicitly in terms of u and v. See, this type of thing will not happen when there is a dependency relationship between u and y. See here, we cannot express x explicitly in terms of u, v, and y explicitly in terms of u and v here. Okay, y explicitly in terms of u and v here. On the other hand, when we have there is no functional dependency, then you can that is when u and v are functionally independent, then you can express this. So in this scenario, we can also think about what is dou xy by dou uv. That also we can think about. So this it says 1 by dou uv by dou xy. That is what it says. Okay, we already found the dou uv by dou xy here. Where did we find that dou uv by dou xy? See here, we have found that dou uv by dou xy. So here, what we need to highlight that. So here we found that dou uv by dou xy, dou uv by dou xy is equal to x. This is an important observation here. From this, it follows that u and v are functionally independent. Now, if you want to find, because we are able to express x and y also in terms of u and v explicitly, so we can in fact write this as 1 by x, that we can write as 1 by x. But what is x? X is 1 by u square plus v square. 1 by u square plus v square. That, so you can write like this. This is, but if you want to see, this is a property. See, what I am saying is that this is a Jacobian property. One important property here that is there in this slide also. See, from here also you can calculate what is dou x dou u dou x dou v, what is dou y dou x dou u dou y dou v, what is dou y dou u dou y dou v. You can calculate that, and the answer you will get is 1 by u square plus v square. For example, see here, I can in fact calculate. Okay, that I'll come to this point later, because I can demonstrate that the way of obtaining this one, the way of obtaining, see, using this formula, you can obtain this. That's what one way. And the other way is you can also obtain like this. One can also, okay, one can also obtain like this. How? See, if you want dou xy by dou uv, then how can that be written? That is determinant of xu, xv, yu, yv. This is how one can write. This is how one can write. So if you write like that, what is xu here? Dou x dou u I am telling. So if you take dou x dou u here, where is that our relationship? See here, dou x dou u, yeah, here I wrote. So you can get dou x dou u here also. Why? How can you get dou x dou u? See, when x square is equal to u square plus v square, can I get dou x dou u? Dou x dou u you can get. See here, I'll write, you have x square is equal to u square plus v square. That implies dou x dou u, in short I am writing, that is 2x dou x dou u. Both sides you are applying dou by dou x. Dou x dou u, I mean dou x dou u. So 2x into dou x dou u is equal to 2u. So your xu is equal to u. So this implies xu is equal to u by x, but you need to express everything in terms of u and v only. So what did I tell you here? When you come over to here, like x is equal to square root of u square plus v square, you only take that value. That is, don't take the negative value here. Implies xu is equal to u by square root of u square plus v square. That's what we have taken. This is dou x dou u. Similarly, from the same relationship, see, I write here, if x square is equal to u square plus v square, Because of the symmetry between u and v, you can get xv is equal to v by square root of u square plus v square. So we got, see here, to fill these gaps, xu, xv we got. Now yu, yv you want. Where is yu, yv? Yeah, our relationship is this. Okay, our relationship is this. So yu, yv, if you want to get, there is an easy way. See, there is an easy way. What is the relationship between relation we are seeing at tan y is equal to v by u. Tan y is equal to v by u. See here, tan y is equal to v by u. Yeah, right. Tan y is equal to v by u. So from this, what can we say? If you want to, with respect to u, if you tan y derivative is secant square y. So secant square y, sorry, secant square y into yu is equal to right side. V is constant. So minus v by u square. So therefore, what is yu? Yu is minus v by u square. Here secant square y is there. Okay, so this is nothing but, okay, this is nothing but is equal to, I can write this as minus v secant is 1 by cos, so cos square y by u square. But see here, you look at the relationship here. Yeah. So what is cos y? Cos y is u by x. Cos y is u by x. Okay. Cos y is u by x. Here it is there. Cos y is u by x. When cos y is u by x, cos square y is u square by x square. So u square by x square. See here I can write this square, this is equal to minus v by u square into u square by x square. That is equal to u square minus v by x square. But what is minus x square? X square is u square plus v square. X square is here. X square is u square plus v square. So this is coming as, okay, just let me finish, minus v by u square plus v square. Very good. So what did we get here? We got yu as, minus v by u square plus v square. We get yu as u square plus v square. Okay, we will highlight this. We can see the problems. Many problems can be done in easy way, but what is the purpose of this Jacobian? I would like to convey. That is why I am giving an example here. Then we directly go to the problem solving session. So, right, this is one thing we need to observe, and one more thing here. It is here good. This is one more observation we have observed. And one more is there here. Yes, this is one more thing we have observed. What else to be computed? We have computed yu. We need to compute yv. Right? That yv also can be obtained from here. Again, we go to tan y is equal to v by u. Again, we go to tan y is equal to v by u. Okay, we'll go tan y is equal to v by u. Again, tan y is equal to v by u. Is it right? Do we have tan y is equal to v by u? Yeah, right. So this implies as before. Now we need to do with respect to v. Earlier we did with respect to u. Now with respect to v. So secant square y into yv is equal to, chain rule we are applying here, 1 by u. So this implies yv is equal to dou y dou v 1 by u secant square y. So this is nothing but secant square means cos square. So you have cos square y by u. But what is cos square y? In the given scenario, cos square y, yeah, cos square y is u square by x square, u square by x square. So this is equal to u square by x square into 1 by u. So it is u by x, but we know that x is square root of u square plus v square. Sorry, here u by, here this is square is there. So u by u square plus v square. Yes, now we are close to the answer. So in fact, not the answer, the very purpose of this discussion. So implies what we have done, yv value. Yv is equal to u by u square plus v square. Right, very good. So now this also needs to be highlighted, because why we are highlighting all these things? See here, I will tell you. We want to calculate this one, dou xy, dou uv. This Jacobian we want to calculate. What is the formula here? xu, xv, yu, yv. This is the formula. Do we know xu? Yes, we have done xu here. Where is that xu? Yeah, it is u by u square plus v square, square root. Okay, u by square root of u square plus v square. So this is u by square root of u square plus v square. Similarly, that is v by square root of u square plus v square. Okay, on the other hand, what is yu is here, minus v by u square plus v square, minus v by u square plus v square, minus v by u square plus v square, and this is u by u square plus v square. Good. Now we'll see what is the determinant here. The determinant here is u square plus v square. Very good. See, you can see u square plus v square by, okay, u square plus v square into square root of u square plus v square. So what we are getting? We are getting this as 1 by square root of u square plus v square. Now see here, this already we got. If you use this property, where here we have used one very nice property. Yeah, this. See, I already got this as 1 by, okay, here square root is missing. Why square root is missing? Why square root is missing here? Just a minute. We got x, sorry, x. Okay. Okay. See here, we need to put here x means square root of x u square plus v square. So without doing all these things, already we got. Where is this? Why? How we got that? Using this property. Using this property, we directly got. But if you want to use the definition, this whole process you have to. Okay. So that is the advantage with the properties. So see here what we have done. So here we introduced the idea of Jacobian. When we have two functions of two variables, that is what we call a transformation. We are moving from XY frame to UE frame. In that a case, in such a case, we are associating a matrix, Jacobian matrix, and it is Ux Uy, Vx Vy. When you are having three functions, that is a determinant of that Jacobian matrix is called Jacobian. And if you have three functions involving three variables, on similar lines, we can talk about the Jacobian matrix and its determinant. And then what is the use of one of the most important uses of Jacobian matrix? Jacobian is the idea of Jacobian is that it decides whether they are functionally dependent or independent. So if the Jacobian is identically equal to 0, then they are functionally dependent. If they are not, if it is not equal to 0, then they are functionally independent. And I have given here an example whereby we can see that there is a functional dependency between u and v, where u is cos x and v is sin x, and that relationship is u square plus v square is equal to 1. On the other hand, if we take in another example, u is equal to cos x, x cos y, and v is equal to x sin y, then the Jacobian becomes x, which is not is equal to identically equal to 0. So therefore, you cannot expect an explicit relationship between u and v, I mean, which does not involve x and y. So they are functionally independent. That is one of the important uses. And one more thing is that if you in a because we know that we can talk about dou uv by dou xy in a similar way. If they are functionally independent, then you can express x and y in terms of u and v, and you can talk about the Jacobian of x and y with respect to uv, and that is equal to the reciprocal of the Jacobian of uv with respect to xy. That is what we have demonstrated here. So these are the important properties of the involving the concept of Jacobian. Now we will go to the problem solving session on Jacobians. So this is the idea that I clearly explained everything here while doing this one. Some properties also I have mentioned here, and then Jacobian of implicit functions. This is, you need not worry much about that one, because in GATE they don't ask these things. Whatever I have told you, it is enough. Okay, this is all about integral calculus. Then we'll after looking at the examples, we look at this extreme values. That is what I planned for today. So right now we go for this application of Jacobian problems involving applications of Jacobian. Yeah, here we are in fact doing already in previous classes. We have done problems involving Taylor series of functions with two variables that we have done, and we have used the we have done some problems by using the Euler's theorem of homogeneous functions. They are the most prominent ones we have so far done. Now we deal with Jacobians. So if we come to Jacobians, yeah, somewhere I have seen here problems. Yeah, right. Right. This is our first problem. 18th problem. X is equal to u into cos v, y is equal to u into sin v. Okay, x is equal to e power u into cos v. X is equal to e power u into cos v, and what else is given? Y is equal to e power u into sin. This is given. Okay, y is equal to e power u into sin. Then we are asked to compute Jacobian of xy with respect to uv. What is the formula? XU, that is dou X dou U. XV, that is dou X dou V. YU, dou Y dou U. YV. This is the formula. So if you take XU, see here X with respect to U, you have U e power U cos V. E power U cos V. E power U cos V. And what is X with respect to V? Minus E power U sin V. And now yu means what is yu is why do you, I mean e power u sin v, e power u sin v. And what is do y do v is e power u cos v. Right, this is equal to, you have e power u cos square v, you can see plus sin square v, and this is equal to e power u, which is not equal to 0, please remember. Okay, so in fact you can say that they are functionally dependent also, independent also. So when it comes to, so the answer is A. For 18th question, the answer is A. Now the second one, the Jacobian dou uv by dou uv is equal to, yeah, this is very, see here, the Jacobian of dou uv by dou uv, what is that Jacobian of dou uv by dou uv? So this is one problem we have completed. Now he is asking for dou uv by dou uv. So what is, how you apply the formula? Here uv. Next vu. Okay. Then this is equal to uu is 1. uv is 0 because dou v is 0. If u is u, v is v. That is the meaning there. Okay. Then dou v dou u. Dou u is is 0. Dou v is 1. So you are getting the answer as 1. So are we getting the answer as 1? That is C. For 18, the answer is C. You can see for 18, I think the answer is C. What is this? He is writing D. There are some errors here. For 18, it is, where is 18? Where is 18? No, I'm asking for 19. For 18, we got A. For 19, we have to get 1. We have to get 1. We have to get for 19 1. 19 means 1 means what? Half he is getting. No, that is not right. It is actually 1. Right. Now next we go for the 20th problem. U is equal to e power x sin y. V is equal to e power x cos y. E power x sin y. Next problem. See, when you ask for this particular question, this means, see, one thing we need to remember when you write like that, u is equal to u, v is equal to v. This is the thing he is talking about here. Okay, so that is why dou u is dou u is 1, dou dou v is 0. Similarly, dou u is 0, dou v is 1. That's why I wrote like that. It is 1. So now next come to the other example here. What is that other example? U is equal to e power x sin y. U is equal to e power x sin y. U is equal to e power x sin y. V is equal to e power x cos y. Okay, we'll see this. Just to let me charge this. Okay, okay, good. Then do I have to see the charging? Just wait for a while. Okay, right now we will see. Right. So in this case, we want what did they ask for? They ask for do uv by do xy. So this is again the formula ux, uy, vx, vy. So this is same as ux is e power x sin y, e power x sin y. We have e power x cos y, e power x cos y. Then vx e power x cos y, e power x cos y. Then you have e power x sin y. Because dou v dou y, see here dou v dou y is minus e power x sin y. So this is equal to, you have e power x as 2x, e power 2x, in fact e power x into e power x is e power 2x into, you have minus sign here, sin square x plus, sorry, sin square y, sin square y plus cos square y. So that amounts to e power minus, sorry, minus e power 2x, minus e power 2x, not is equal to 0. E power x into e power x will be there, so e power 2x will be there. So that is the Jacobian here. So e power minus 2x, where is that? Yeah, e power minus 2x into sin y cos y, he is saying. E power minus sin square y will come minus cos square y. So minus, if I take e power minus 2x should come. Again, please check once. E power x sin y, very good. E power x cos y, very good. Dou u dou x means e power x sin y. Dou u dou y e power x cos y. Dou v dou x e power x cos y. Dou v dou y minus e power x sin y. So e power x into e power x is e power 2x. and sin y into sin y is sin square y. There is a minus sign, minus of e power x cos y into e power x cos y is e power 2x into cos square y. So e power minus 2x will be the answer. There is no doubt. Okay, that will be the answer. Just let me see here. What is our first? Yeah, here a small thing. You have to put 2u here. That is what I'm saying. Because e power u into e power u is e power 2u. That is e power. Okay? E power u into e power u is e power 2. Done? Good. So this will be the answer. Next problem. Two functions u and v are functionally dependent if the Jacobian is equal to 0. That is correct. D is the answer. Next, u is equal to sin x plus sin y. V is equal to sin x plus y. Okay, u is equal to sin x plus sin y. What is happening here? Okay, u is equal to sin x plus sin y. V is equal to sin x plus y. So in this case, I'll directly write what is ux. Ux is cos x. What is ui? Do y, I mean cos y. What is vx? Vx is cos x plus y. What is vy? Again cos x plus y. So if you take the Jacobian j, sorry, j, I mean, how you are is equal to dou uv by dou xy, dou uv by dou xy. Okay, this is equal to ux, uy, vx, vy. This is equal to cos x, cos y, cos x, cos y, 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 cos x plus y. Very nice. So, what will be the answer here? Right. So, this is equal to cos x plus y, okay, into cos x minus cos y. Cos x plus y into cos x minus cos y. So these they are not in fact they are not, this is not equal to 0. That can never be 0. So therefore what can we say? Therefore u and v are functionally independent. Therefore they are functionally independent. So see here, functionally independent. 22 it is B. Now see, u is x sin y, v is y sin x, then is equal to u is x sin y. Okay, v is y sin x. Y sin x. So here I want what is ux. Ux is sine y. What is uy? X cos y. What is vx? Y cos x. What is vy? Sin x. Sin x. So therefore, do you by the x is equal to ux, uy, vx, vy, vx, vy. So this is nothing but sin y, x cos y, sin y, x cos y, sin y, x cos y, vx, y cos x, y cos x, sin x, y cos x, sin x. Right? Okay, sin x. So this is equal to, okay, sin square x minus xy into cos x cos. Is it? Yeah, sorry, not sin square x here. It is sin x. Sorry, sin x sin. Yeah, this is what we are. Minus xy into cos x cos y. So yeah, that is D 23D. Taylor series we have done, already completed the topic. This also comes. Hello. Yeah. Tell me.
Sir,
Vinay,
the previous question, sir.
which
Uh,
question? Can we
uh,
scroll that? Okay.
yes, sir.
Uh, yeah, tell me, Vinay. 19, 20.
Sir, can you go to the solution? Solution. What you did.
This one, 23. Ah.
U equal to sin x plus sin y.
Okay, okay.
One
Sin
second.
x plus sin y. Yeah, right. 22nd question.
Yeah, sir.
Is
That
it right?
solution. Uh,
You want solution?
yes, sir.
Ah, just sin x plus sin.
The previous one from this.
Ah, yeah. See
Yes,
here.
sir.
U
Here.
is equal to sin x plus sin y. Is it right? Let me see. U is equal to sin x plus sin y. V is equal to sin x plus y. Okay.
Yes, sir.
Ux is cos x. Uy is cos y.
I got this, sir. The last step. You told it is not equal to zero, no, sir. How is it, sir? Like,
Oh, good, good, good. Right. That is what. Yeah, okay, okay, good.
yes, sir.
See, yeah, you are right. That's a good question. When can this be equal to? See, okay, got. Good question. Very good question. You are in which branch? When I tell me, just I would like to know out of my interest.
Sir, mechanicals.
Good, very good. Okay, right. I'll come to that. Right. See, you have this is A, this is B. Okay. A into B is equal to 0 means either A is 0 or B is 0. Right?
Yes, sir.
Both is 0 is 0. Both cannot be 0. See, because if you have cos x and cos y equal, okay, cos that is what I would like to say. See, you are saying is equal to 0 means what? identically equal to 0 for all xy. That is the meaning. Please remember here. If for this to be equal to 0 means, what I am saying is that for every choice of x and y, it should be equal to 0. For example, if I take x and y as 1, if I take x and y as 1, then cos x and cos y are same. Cos 1 minus cos 1 is 0. Fine. Okay. I will take a choice. Okay. Just wait. Uh, good. Wait. I have to take some different ones here. Good. So if you take x as uh, x as 0 and y as pi, sorry, y as pi by 2, y as pi by 2, x as 0 and y as pi by 2. So what is this one? This becomes cos pi by 2. Is it right? Cos pi by 2 is 0. No, okay. No, one should not get this as 0. How can we do that? Okay, I will come to that. Just we'll go to the here, right? So we have cos x plus y into cos x minus cos y. Some choice I have to show. For some choice of x and y, this is not equal to 0. I have to show. Okay. So if I choose x and y as pi by 2, that is not my choice. So how can I show? I have to choose one choice here. So if I choose x as okay, what is there in this? If I choose as x as 1 and y as 0, what will happen? I will get cos 1, cos 1 into cos 1 minus cos 0. Cos 0 is 1. So you have cos 1 is not equal to 0, that we are sure. And cos 1 is not equal to 1. Cos 0 is 1. Cos 1 is not equal to 1. Therefore, this for the choice of x is equal to 1 and y is equal to 0, for this choice, your cos x plus y into cos x minus cos y is not equal to 0. Therefore, this is not equal to 0. This is not equal to 0. I see. See, not equal to 0, negation is equal to 0 means identically equal to 0 for all xy. That is the meaning. Identically equal to 0 for all xy. Here I told at the beginning. Yeah. See, when I am saying here equal to 0 means for every choice, this is a function of x and y. For every choice of x and y, it must be equal to 0. That is why, see, I have given an example here. If you take u is equal to cos x and v is equal to sin y, then we calculated and d is equal to 0. See, so for every, if you take x as some number, y as some number, for every choice it is becoming 0. That is why they are functionally dependent. See, the dependency is u square plus v square is equal to 1. On the other hand, you will not get, see, if you take this as your choice, you are not getting, see, you are getting x here. X means if I take x as 1 and y as 0 here, if x as 1 and y as 0, then my Jacobian is 1, not equal to 0. So for some choice, it is not equal to 0. Therefore, that functionally independent. Is it clear, Vinay?
Yes,
Is
sir, I
it?
got it.
Right. So right, where are we? This Taylor series we have done. This is also we have seen. Now come out to here. The Jacobian for the function u is equal to e power x sin y, v is equal to is equal to. This is also a similar problem. here u is equal to here u is equal to e power x sin y, e power x sin y, and v is equal to x plus log sin y. So ux is e power x sin y, uy is u e power x cos y, and vx is 1. Okay, vx is 1 plus 1 by sin y by x into chain rule. Here y by x is minus y by x square, that is vx, and vy is vy is what is vy here? 1 by sin y by x, 1 by sin y by x, 1 by sin y by x, y into 1 by x. So this is nothing but 1 by x sin y by x. That is okay, good. Now, so what is our Jacobian? So our Jacobian here, dou uv by dou xy, dou uv by dou xy is ux, uy, vx, vy, right? So this is, what is your ux? Ex sin y, e power x sin y, okay, e power x sin y, e power x cos y, and you have 1 minus 1 minus y by x square, y by x square sin y by x square sin y by x, and then this is 1 by x sin y by x, 1 by x sin y by x, and you have this determinant. So this is equal to, so you have e power x sin y by e power x sin y by e power x sin y by x sin y by x sin y by x sin y by x, okay, into e power x cos y, e power x cos y, so minus e power x cos y into e power x cos y into e power x cos y into 1 minus y by x square, 1 minus y by x square sin y by x. So is there any simplification possible here? Right. So you have this is equal to not so the LCM, if you look at the LCM, you have x sin y by x. So you if you take x square is of much use. I think what are the choices here? It is better to see before going for simplification. So it is 1 0 e power x by x. So simple he is giving 1 0 sin x sin y minus x. Okay, I think we require simplification here, right? Anyway, so what, what is the simplification you get here? E power x sin, I will do one thing. Better to take LCM here. So e power x by x sin y by x we will take common. E power x by x sine y by x we will take common. That is better. Then, then our first term here. Okay, e power, so you have sine y. This is sine y minus, you have minus here, sine y minus, uh, you have, yeah, right, cos y, sine y minus cos y into, cos y into, cos y by x is there. Okay, by x into, by x into, x square sine y by x minus y, x square sine y by x minus y, x square sine y by x minus y. This is what we are getting. Okay. Can this be further simplified? So minus, what is that? Y by x, y by x cos y is there. No, I am not able to get a simplified thing here. So upon simplification, what we can get, e power x by x sine y by x, e power x by x sine y by x, y by x, and say start sine y, okay, minus sine y minus, here what we do is that first term will be x will go, so x cos y sine y by x cos y sine y by x minus x cos y, okay, I better write x cos y like this, minus x cos y, x cos y sine y by x, sine y by x, right? X cos y sine y by x minus y is there, minus y cos y by x, minus y cos y by x, minus, is it right? Minus y minus plus, plus y cos y by x, plus y cos y by x, plus y cos y by x. Right, let me see then. What is this? Can this be simplified? You have to look at these things here, the relationships. So e power x sine y is x log, no such relationship. How simple? How can this be simplified? You cannot simplify this. How can we simplify this? Wait for, did I take it correctly? Just e power x sine y, x plus log sine y, x plus log sine y, x plus log sine y. Oh, sine y by x I took sine y only. This is, oh no, no, sine y, right? Log sine y. What is log sine y? Why I got y by x here? Shoot, this. This. Why I got? What is the problem here? Small mistake I have done. Oh, this is only sine y. The mistake I did is here. This is not there. Okay, no problem. Y. This is y. Okay. Then ux, uy is there. Fine. Here the mistake is vx is equal to 1 by sine y only. Right. 1 by sine y. And what is that? Vx with respect to vx if I am doing. Yeah. Vx, Vx1, this will not be there. This whole term will not be there. V is 1, that's the problem. Y by x I took, right. And here Vy means, yeah, here only Vy will come. So 1 by sine y into cos y. 1 by sine y into cos y. So here 1 by sine y, 1 by sine y into sine y, it is the derivative is cos y. So cos y, I have to write here cos y. Good. And this is not there. It is this mistake. So this is equal to cot y. Okay. Sin y is cos y. So Vx, Vy also we have calculated. Now there is a mistake here. This we will erase better. This we will erase. So I will erase this whole part. This is wrong. It's not coming. Erase is not coming. Right. Good. And so we remove this. Anything is there? Yeah, this also we don't want. Small mistake we have done. Delete this. Okay. This also we want to delete. So this is there. Right. This is also not there. Right. So this is also not there. Right. So when I come here, right. Ux is e power x sin y. Ux is e power x sin y. E power x sin y. And here uy is e power x cos y. Uy is e power x cos y. And Vx is 1. Vx is 1. And this is cot y. So this is equal to e power x sin y cot y, e power x sin y cot y minus sin y cot y minus e power x cos y, cos y, e power x cos y. So this is nothing but 0. This is 0. So they are, yeah, 0. So 0 is C is the answer. So I think problems on Jacobian are complete now. Okay. Now we go for maxima minima, right? So maxima minima problems, extreme values. So this is the slide. This is the slide. Just a minute. Okay. So now we look at maxima minima. Quickly we'll go for that. So here when it comes to maxima minima, two variables are there. So what first step is that, right? Good. We'll see. Or yes and D. Very good. Okay. So how can we deal with maxima minima? So given a function of two variables, now first step is that, so this is a real valued function. So the first step is you compute fx, dou x I mean, make it equal to 0, fy, make it equal to 0, solve for x and y. So what is x, what is y, find. You find from these two equations, the first step is to find x and y. Let x and y be, suppose, a b. X is a, y is b. Then what we need to do is that you find f xx, dou square f by dou x square. And in that you put xy as ab. This you say r, that is a number. Similarly, s is equal to dou square f by dou x dou y. Dou square f by dou x dou y, right? S is that. So this is also at xy is equal to a comma b. You find it and you say that is yes. Then t is equal to dou square f by dou y square. Then find that xy is equal to ab. So now what we got? We got r value. So we found, see, look at, so observe the signs of, or observe the signs of, see, observe the signs of r and here r and rt minus s square. R and rt minus s square. Observe the signs of r comma rt minus s square. That's all. Signs only. If, now you look at the argument. If rt minus s square is greater than 0 and r is less than 0, then fxy has maximum at xy. If rt minus s square is greater than 0, see, both it should be greater than 0. If r is greater than 0, then fxy has maximum at AB, a minimum at AB. So if r is less than 0, it is maximum. If r is greater than 0, it is minimum, provided that rt minus s square is always greater than 0. In other cases, that is rt minus s square, either it may be less than 0 or is equal to 0. In both the cases, you cannot draw any conclusion. That is, in particular, if it is equal to 0, we cannot draw any conclusion. But if it is less than 0, you can say it has a saddle point at AB. That's all. So now we go to the so what are the conclusions here we are saying? Just see the sign of RT minus, just see, okay, the sign of RT minus S square. What are the possibilities here? You remember like this. It can be greater than 0. It can be greater than 0. It can be less than 0. It can be equal to 0. If it is equal to 0, no conclusion. Don't go for any other observation. If it is less than 0, it is saddle point. Straight away say saddle point. And if it is greater than 0, you have two choices. Now whether r is less than 0 or is greater than 0. See here. If r is less than 0, f has maximum. If r is less than 0, f has maximum. So in this case, f has maximum. In this case, f has minimum. That's all. These are the cases. Now we'll go to solve some problems.
Sir, what do you mean by saddle point, sir?
Saddle point means, see here, I will tell with one variable, see, one variable, then you can understand. If you have a function x and y, see here, the scenario is if something like this is there, see. At this point, you can say maximum is there, maximum value in this neighborhood. See, this is neighborhood. This peak, this is the value. See, suppose if you want at this point, the y value, it is here. But at this point, the value is here. This value is less than this value. So at this point, it has maximum. Similarly, you can talk about minimum. But sometimes what may happen is that the scenario will be like this. See here. Of 8, 8, 9. So the scenario, see here, I'll show this. Wait. Sorry. Okay. Yeah, good. Suppose the function is like this, see here. Okay. Here, again, I will draw with care. Suppose something like this. In this case, you do not have maximum or minimum. See here, for example, at this particular point, to the left of this, the graph is below this line. To the right of this, the graph is above the line. So, but you are able to see some kind of tangent is there. At this point, y dash x is equal to 0. Please remember that. Y dash x is 0 here. That is, you are able to draw tangent, but this to the tangent line to the left, this whole part, this part is below this tangent line, and to the right, it is above the tangent line. This is called saddle point. On the other hand, you look here, at this maximum, if you draw the tangent, the curve here, the curve here, I mean in this neighborhood, it is to the one side of this one. But here, if you draw it is in the other side. So usually when maximum or minimum you are noticing, the curve is locally to the full curve is locally to either top side or below that. But in saddle point, some part will be above and some part will be below. So when we are going for in functions involving two variables, you have x and y. F of xy will be observed in z axis. So you have a surface. If this surface at this point, see xy, the whole surface to tangent plane you can think about, it will be below. But if a surface is like this, then to the tangent plane, in that surroundings, some part will be above. But there may be a surface like this. In this, some part will be above and some part will be below. That is called saddle point. Are you able to get that,
Yes, sir. Got
Vinay?
it.
Right. So that is saddle point, right? Okay, we go now to see if you. I don't know. You look for if you are interested. These questions are they are not giving. I'll tell you where somewhere I have I think removed that slide. Did I remove? Yeah, because I removed. I think it may confuse. That's why I removed that slide. Let's see. No, no, I removed that slide. Or yeah, I removed. In fact, I'll in, at an appropriate time I will tell you. Okay, fine. Now we'll go to directly to problems, right? So here, yeah, right. Uh, So we are reaching integrals. Here we'll see. With usual notations, a function fxy has a maximum at AB. Direct question. This is from the definition. We go to the labeled ones. Gate. Okay. The curve given by the equation x cube plus y cube is equal to 3axy is symmetrical about x-axis. No, I don't go for symmetries. That we can talk separately. Maxima and minima. Yes. So fx is equal to 2x cube plus 15x square. Fxy is equal to 2x cube plus 15x square. Okay. 36x plus 10. Then we have fx is 6x, sorry, 6x square plus 30x plus 36. What is fy? Fy is 0. Fy is 0. Did I write the question correctly? Right. Fy is 0. Very good. So now see, we want to find okay. Now we need to now we need to solve this. We need to solve these two equations. Which equations? These two equations. This is equal to 0. We have to see. So fy is 0. Anyways, fy is 0. Nothing is there. Only for 6x square plus 30x plus 36 is equal to 0. That implies, so this implies 6x square, that is x square plus 5x plus 6 is equal to 0, means x is equal to 236. So minus 2 comma minus 3. And now see what is happening. What is y value? Y can be anything. That is, y can be anything. Y can be anything. Please remember. Okay. Now, because there is no involvement in y here. Y is a free variable here. So now we need to calculate what is r, fxx. Fxx is here, fxx. So 12x plus 30. 12x plus 30. Right? And what is fyy? That is anyway 0. Fxy, that is also 0. Fine. So now r is equal to fxx at that point, at xx at ab, I mean. B is anything. See, I told y is anything, but the choice for A is only 2, minus 2 and minus 3. But for minus 2 and minus 3, if you take minus 2, minus 24 positive, minus 3. So, right, good. So, if your A is minus 2 and A is minus 3, A is minus 2 means what is happening here? Minus 2, 24. So, it is positive. R is greater than 0. Okay. And T is, sorry, R is greater than 0. If B is minus 3, minus 36, so this is less than 0. Right. Now, RT, T we have to see. So, T is, so RT, T is equal to RST, FYY at AB. That is anyway 0. Okay. Then S is FXY. That is also 0. Now, what did I say? Uh, what is that condition I told? So it is, I have written here. Uh, RT minus S square. RT minus S square. RT minus S square is 0 here. RT minus S square is 0. So you cannot draw any conclusion. That is the thing here. So what did he say here? Maxima and minima of the function. You cannot draw any conclusion here because there is something wrong here. RT minus X square. Usually what they will do is that in this case X is 3 and X is 2. No, he cannot. There is something wrong here. So this problem, there is something wrong in copying. Then sixth problem. Sixth problem, I think we will get 2x square plus 2xy minus y cube. Something, no conclusion here for this problem according to the data, previous problem. So here, so what is it? Okay, all right. So, where is that? 2x square plus 2xy, 2x square plus 2xy, 2x, 2x square plus 2xy, 2x square plus 2xy minus y cube. This is f of xy. Okay, now fx quick. Fx is 4x plus y, 2y, 4x plus 2y, 4x plus 2y. What is fy? Fy is equal to fy, I want fy. 2y minus 3y square. 2y minus 3y square. 2y minus 3y square. Is it right? 2y minus 3y square. Fy. Fy is 2x minus 3y square. Sorry. 2x minus 3y square. 2x minus, yeah, x minus 3y square. And fx is correct, 4x plus 2y. 4x plus 2y. 4x plus 2y. Oh, so okay, 4x plus 2y. So this is equal to 0. This is equal to 0 if I take. So how can we solve? Good. We can solve these things first. We have to solve these things. So okay. How can we? So here, what can we say this implies? 2x plus y is equal to 0 and 3x is equal to 3y square, right? Okay, 3x is equal to 3y square. So if we take again these two things simultaneously, we can say y is equal to minus 2x. So 3x is equal to y is equal to minus 2x from the first equation.
2x equal to
So
3
sorry, what did you say?
2x equal to 3y square, no sir? Can you check that again?
X is equal to first fx is fi are same. Is it correct?
Yes, sir. Starting is correct.
uh, and
After
2x plus y is equal to 0, that is right, no? Oh, okay, this is
yeah,
2x.
2x, sir.
Right, I got. Okay, 2x, this is 2x, right. 2x is equal to 3y square. So this is also I want to correct. ah so here 2x is equal to, now if I take y is equal to minus 2x, 3 into 3 into y is equal to minus 2x whole square, right? So 4 12, so 12x square here, 4, yes, 12x square, right? um, right, good. So 12x square is equal to 2x. So what I am getting here, then from this, see, remember always one thing, when I converted this into single equation, there is a relationship here. That is sailing, we are sailing with that relationship. What is that? 2x plus y is equal to 0. That is there. This is already there, in fact, which is not visible here. So this implies, okay, x is equal to 6x square. Anyway, this 2x plus y is equal to 0 is there. So this implies x is equal to 0. I mean, see, you are writing like this. 6x minus 1 into x is equal to 0, and you have 2x plus y is equal to 0. That is there. So now you can say that implies x is equal to 0. If x is 0, y is also 0. That is one choice, because 2x plus y is equal to 0. And another is x is equal to 1 by 6. Okay. And y is, x is 1 by 6 means 1 by 3. Y is minus 1 by 3. This is another choice. So we have two choices now. We have two choices. So for this, we need to calculate what is fxx quickly. fxx. fxx is here, fxx. It is fxx. fxx is 4. 4. fxy is, sorry, fxy. Where is our fxy? fxy is 2. Good. fxy is 2. And fyy is fyy. Where is fyy? fyy is minus 6y. Minus 6y. Now see, it is very right. I'll do one thing. I write r s t directly. Here two choices are there for xy. That is my ab's. What are they? They are, here I have written 0 0 1 by 6 minus 1 by 3. 0 0 1 is 0 0 is one choice. 1 by 6 minus 1 by 3 is another choice. Okay, 1 by 6. Yeah, right. Now R value. R means fxx at this. It is always 4. So here 4, here 4. Yes. When you take S or ST, S is fxy. So that is 2. because it is a constant, you have to write 2 2 only. There will be no change here. 2 2. That is fxy. Now when it comes to fyy minus 6y. So here minus 6y means because y is 0, you are getting 0. Minus 6y. Minus into minus 6 into 1 by 3. So you are getting 2 here. So now you just simply RT minus S square. Is it right? It is RT minus S square, I think. Yeah, it is anyway in my, here also we have RT minus S square. Is it right? Where is that? RT minus S. No, no. Some arrows. Ah, yes. RT minus S square. Good. RT minus S square. RT minus S square in this case is RT minus S square. Minus 4 this is, and this is RT 8 minus S square is 4. So see here, the choice is here, because RT minus S square should be positive. If it is negative, so you can conclude that here R is greater than, so at this point it is minimum, and this is a saddle point. 1 by 6 minus 1 by 3 is minimum, because RT minus S square is greater than 0. Here RT minus S square is greater than 0. There is that, yeah. And R is less than 0. Then it is maximum. R is greater than 0, it is minimum. R is greater than 0 is there here. So it is minimum. R is greater than 0, it is there. So it is minimum here. At this point, it is minimum. And this is saddle, because you have less than 0, this is saddle. That's the conclusion. I think, yeah. 1 by 6 minus 3 minus 1 by 3. They are stationary points. Yes, good. 2 stationary points, 0, 0. So first is the answer. Answer is 2 stationary points, 0, 0. Stationary means f dash xy is f dash of x is fx is 0, fy is 0. Every solution for that is called a stationary point. So 0, 0, and this, I mean, what I mean to say is that, see, what I mean to say is that both are stationary points. When can we say a point is stationary point? Simply, if you have this, here I told you the properties. Yeah, anything that satisfies this, yes, right. Anything that satisfies this, that is this one, is a stationary point. If you solve that equations, you will get a solution that is called a stationary point. Once it is decided as stationary point, then it may become an extreme point, that is a maximum point or a minimum point or a saddle point. That's all. So yeah, we will stop and we'll see in the next class. If some problems are there, we'll see. For now, we'll stop, and next class we'll see some more problems on maxima, minima, and then we shift to integration. So that's all for today. Any questions, Vinay? You are the only. If you have any questions, you can now. You are welcome.
No questions, sir.
Right. We'll see in the next class. Probably tomorrow at the same time I'll plan. If you join, it is good, because we are lagging behind. That's why I have uploaded 4 videos there already. I'll share the link anyway if you want. Okay. Bye then. Thank you.
Sir, can you share the drive link, sir, now?
Now you want the drive link. Are you there in the classroom? Can you please see this classroom is there? Are you there in this classroom?
I think so. I'll just check, sir, 1 minute.
You do one thing. I will share all the links in the YouTube with you. But in this classroom drive, I am updating the PPTs and the material.
Yes, sir.
That's the only thing.
I'm there. I'm there, sir. I'm there in the classroom.
If you are there, you just look at the folder. In that one, I will update. I think I forgot to update 4 videos here. I will do by tonight. Okay. Tomorrow you can see all the PPTs. Tomorrow morning, all the PPTs and whatever I have shared, recorded in the videos, everything you can find there. Okay.
Thank you, sir.
All right.
Okay.